can we wait for at least another 5 minutes because six people are ready.
Yes, yes, please. That's a good
Oh,
idea. So we can do that. Yes, we can do that. We can do that.
yeah.
That's a good idea. Yeah.
Okay.
So, I mean, when you talk to the students, I mean, you can tell them about the plan. I mean, I know for a typical KNUST student, they know you never run regression until you are in maybe final year or until you do it yourself. You just
Yeah,
do the
yeah,
theory,
yeah,
you just do the theory, and that's how it is, right? So maybe
yeah.
when you talk to some of these students, you can introduce them to the idea of economics weekly, whereby there are resource persons there who can help them in terms of like I know the department organizes a status seminar, every year, but that's mostly for final year students and the TAs. So
Yeah.
maybe they will learn one or two things here.
Okay.
And I think it's almost this 310, right? Yeah, I said 310. I think it's almost 3. It's almost 8:10, right? You can start whenever you're ready. Okay, bro. I think it's almost three. It's almost 8:10, right? You can
Yeah.
start whenever you're ready. Please, you can start whenever you're ready.
Okay. So can you see?
Yes, we can see.
Oh, okay. Hello. Oh,
Gabriel, we can see your screen, but we can't see it again. Can you share it again?
okay. Can you see it? Hello. Is it fine?
Yes, we can. Yes, we can see it. You can start.
Oh,
You
okay.
can see.
Oh, please, Ajo man, can you please mute yourself? Hello. Okay, thank you. Okay, good evening and maybe good afternoon to everyone, and welcome to the first session. And my name is Gabriel Ofori, and I'm currently a teaching assistant at the Department of Economics. Okay, so this session will be about introduction to econometrics, and as the title says, it's just going to be just an introduction, and we are not going to dwell much on the mathematics and anything to scare anybody off. So I hope this session becomes more intuitive and more understandable. So I hope you stay with me. Okay. So first of all, this session is usually tilted towards research and not exam. So please, I'm not going to help you to pass your exams. This is more or less like a research course. So I hope you don't have maybe the wrong idea about this, but it's going to be about research, research, research. So let's say as a researcher, you have an idea, you want to research about a phenomenon. For example, maybe what will happen to unemployment in Ghana if the government decides to increase minimum rate, or when is inflation harmful? Does class size affect test scores? How does CEO compensation affect stock performance? Suppose you are an analyst and you are being called to analyze the CEO compensation and stock performance. How are you going to go about this? Okay, so these are the kind of questions that we will try and answer, and we are going to use tools in econometrics and try and maybe quantify these kinds of relationships. But in order to do so, we need to resort to data, obviously, because we are empirical economics. When you say empirical, it means we are going to resort to data all the time. We are not theoretical economics. So we are going to use data. And how are we going to analyze these kinds of data? We are going to use tools and methods economists have developed over the years, and we usually call it econometrics. So what's econometrics? So econometrics is the application of mathematics and statistical methods to analyze social and economic data. So, oh, hello, can you see my screen? Hello.
Yes, we can see your screen. Please continue. Yes.
Um,
Yeah, Gabriel, you are clear. Please continue. We can see your screen.
oh, sure. I'm coming. Can you still see it?
Yeah, it is. It is. We can see it. Please continue. We
Oh,
can see
okay,
it.
okay. Sure. So econometrics is the application of mathematics and statistical methods to social and economic data. So we are going to apply mathematics and statistics to social and economic data and analyze and maybe draw some inference from these kinds of data that we have. And you've seen mathematics, you've seen statistics, but here we are going to do some practical things here. We are going to result in intuition of these methods and how to apply tools like stata and maybe in the subsequent series, maybe we extend it to maybe R or whatever. Okay. So what does econometrics do? Basically, we try to infer some causal relationship. We want to find out if some variable affects another variable. Another thing that econometricians or econometrics does is prediction, trying to forecast another variable, what would be the future value of another variable. So for example, IMF could come up with maybe some estimates, growth rate for the next quarter, maybe inflation for the next quarter or next year. They use econometrics tools to predict these variables. But most often, we are interested in causal relationship. Why? Because we usually want to advise policymakers on what to do next. So in this session, we are going to focus mostly on causal relationship, trying to find out if one variable affects the other. Note that data will be the talking point because everything starts from the data and the question that we are asking. And then we apply the econometric tool to them. We are not going to start from the tools and then look for data. We are going to start from the question and the data and we apply the tools. Okay, so more broadly, we have two types of economic data. The first one is experimental data, and this is the kind of data that is generated from experiments. Yes, in economics, we conduct experiments, and the most common one is the RCT, randomized control trial or randomized clinical trial, and it's very popular in development economics. The next kind of data is observational data, where we observe subjects in our data, then we collect them. Like we look at individuals, we collect their income, their consumption, everything. And this is the most popular economics because RCTs conducting experiment is very daunting, very difficult, and very expensive. So usually we resort to observational data, and that's what we are going to resort to. I hope in the future, maybe we'll resort to or try to learn about randomized control trial and how ideal that experiment is. Okay, so focusing on observational data, we have types of observational data. The first one is the cross-sectional data. And this kind of data is more about different subjects at a particular point in time. So we can collect data about or on individuals present now and maybe their income, their consumption, or whatever at this particular point in time. And that kind of data is cross-sectional data because it is across individuals and at a specific time. Another type of data is time series data, and this focuses on one subject as opposed to cross-sectional data that focuses on several subjects at a particular time. Time series focuses on the same subjects across periods. So for example, macro data, we can collect data on announced inflation and economic growth from maybe 2005 to 2026. And that's a time series data. Or the time shouldn't always be years, it can be days, it can be hours, like financial data, stock market performance, and all that. So that's time series data, but the subject must be one. And the combination of both is panel data, where you combine the cross-section and time series. That is, the data is across individuals and across periods. So this this distinction is very important because cross-sectional data has the methods that works best for it, and time series too, and panel data. You cannot like mix them up. So it depends on the data and the kind of question that you're asking, that you choose the kind of method that you are going to use, right? Okay. So we know our data, we know everything, we know our question. How should we go about it? So this kind of the nitty-gritty of everything. So the next thing is usually you write down a model. And the most popular one that we are going to resort to first is the simple linear regression model. And this is how we write it. Y is a function of beta naught plus beta 1 x plus epsilon. You can put any variable there, v or whatever. But the y usually represents or almost represents the dependent variable. That is the variable that is being affected. So in your question that you ask, you think about it. Which variable is being affected that I'm trying to analyze? So that variable will be y. And then the x will be the independent variable. And that variable is the variable that's affecting the y, which is the dependent variable. So all this depends on the kind of question that you're asking yourself and you are trying to analyze. Which one is the dependent variable and which one is the independent variable? And the epsilon here is the error term. And it captures all the variables that affect y, but it's not included explicitly in this regression model. So it contains all other variables that affect y. All variables unobservable, the one that we can observe, they are all captured in here. And this is a simple linear regression model because the variables are only two. So it is a simple or bivariate. And it's linear because the betas are all linear. They enter linearly. There is a reason why we are focusing on the betas, and it's because those are the parameters that we are going to estimate. So that's why the linearity is based upon the betas, beta naught and beta 1. Okay, so beta naught is the intercept from our mathematics. Y is equal to mx plus c. The c is beta naught, the intercept, and beta 1 is the slope coefficient. Okay, so let's do some applications. Oh, but before that, okay, let me come back. Let's say we have a consumption function. We want to find out how income affects consumption. How should you model it? How should you write down your simple linear regression model? So income is affecting consumption. So obviously, consumption will be our dependent variable. It depends on our income. Yeah, some people may think that, okay, income may also depend on consumption, but to make things simple, we are assuming that consumption depends on income. And income obviously will also be our independent variable because it is affecting our consumption. And all other variables that affect consumption will be here, will be found in the error term here. All other variables, any other variable that you can think of that affect consumption will be captured by the error term. Another example is class size. So we want to find out how class size, how big it is, affects the test score, average test score. So the variable that has been affected is the test score. So that will be the dependent variable. And the variable that is affecting something else is the independent variable. And all else is captured by the error term. And lastly, if you want to find out whether minimum wage affects unemployment, obviously unemployment will be our dependent variable and minimum wage will be our independent variable. So you get data on all these variables, then you run a regression. Okay, but before that, let's go back a little. This simple linear regression model can be broken down into two, and usually we call it the conditional expectation decomposition. There is a theorem that really captures this. And the beta, this part of that linear regression model, tentatively represents the conditional expectation function. And this function gives us the average value of y given a particular value of x. So we can decide to fix maybe x is equal to 20. The value that will come out of this function will be the conditional expectation value of y. That is the average value of y, given that x is equal to maybe 20. And this is very, very important because those of you who are really, really interested in machine learning and all that, this is very important because it represents the minimization of the regression function. When you minimize the error, this is the function that comes out. This is the best predictor of the y. Okay. So to continue, so we have written down our linear regression model, simple linear regression model. What should we do now? That shouldn't be the end. We need to estimate it. And what should we estimate? Usually we are interested in estimating the betas that we have. So going back, the beta naught and beta 1, we are interested in estimating these beta 1, beta naught. That is getting the values for beta naught and beta 1. That's the mean of estimation. And we have a lot of estimation techniques in econometrics. We have OLS, which is the most popular one because of its desirable properties that we have. And we have maximum likelihood estimation method of moments. There are plenty. And it depends on the situation and some assumption that you are willing to make, which we are not going to tackle here because this is just an introduction. So I hope subsequent series will maybe get into that and maybe later, as we said, we'll relax them and maybe see the way forward. So in this first section, we are going to start with ordinary least squares method of estimation, which is OLS. And it's a kind of estimation that is used to get the betas and beta naught in our simple linear regression model. Okay, so how does OLS go about estimating our beta naught and beta 1? Okay, so for beta naught, you know, the dependent variable is y and our independent variable is x. So it averages the y, which is the y bar, the average of y, and also averages the x, which is the x bar. So the average of x and the average of y. So beta naught will be equal to the average of y minus the beta 1 estimate. So when you see the hat, it means the estimate, the values that we estimated actually, times the mean of x. So when you deduct it, you get your value for beta naught. That's it. And for beta 1, yes, it's very complicated. You subtract the mean from the x and the mean of y from the y, then we multiply them, and then we sum across. Then the denominator will be similar to this, but we square it and then we sum. So let's see how this comes out in terms of an example. So suppose that the mean of x is 3 and the mean of y is 16. And our data is cross-section, which is I. When you see I, it means we are dealing with cross-sectional data. When you see IT, then it means 2. I and T is time series, IT is panel data. So for now, OLS, we are restricting ourselves to cross-sectional data. Individual 1 up to 5. And the value for X, the first individual is 1, 2, similar, respectively. And Y, we know our Y bar, we know our X bar. So when you subtract the mean of X from the X, you get the deviation for what X. And when you subtract the mean of Y from Y, you get the deviation for Y. And when you sum the deviation, you get 0. Then you multiply this -2 times -2. We are finding beta naught, beta 1. Then we use that beta 1 to find beta naught because in the formula for beta naught, you need to first find beta 1. Okay, so after multiplying all of them from the formula, you sum everything. When you sum everything, you get what? 20. That's for the numerator for beta 1. And then for the deviation of x, you square everything. When you square -2, you get 4. So all the values are here. Then you sum everything, then you get 10. So 20 divided by 10. So our value for beta 1 is what? 2. So we've been able to estimate our beta 1. Additionally, after getting our beta 1, the job becomes a little bit easier because we already have our Y bar and we have our X bar. So we fix the values. Y bar is 16, X bar is what, 3, and you got our beta 1 to be 2. So we get the value is for what, beta 1 to be 10. Obviously, you can see that it's very tedious. For when you have a large set of data, then you are going to struggle. So that's why we usually resort to these kinds of tools, course data, and the rest. This is the process that those applications go through. So now we know the mechanism of OLS. So we'll be able to really reason with it. Okay, so let's rewrite everything again and see how they come up. So our beta naught is what? 10. Our beta 1 is what? 2. So we've been able to estimate or fit our regression line. We call this the regression line. It's kind of a line. So y is equal to mx plus c. So the 2 will be the m and c will be 10. Right? It's like a line. So we are done with estimation. We've been able to get our values and everything. Of course, this is very simple. This is very simplistic. As we move forward, we'll be enlarging everything and things will become a little bit complicated, but this is just an introduction. Okay, so we know everything. We've been able to estimate it. What should we do? We are economists. We are not mathematicians or statisticians. We cannot leave everything here. We have to interpret them. So how should we go about it? So let's go back to our normal regression model. Initially, I said we are super interested in causal interpretations, how one variable affects the other. We can resort to prediction. It's also very important, but usually all our analysis are based on policy. We want to recommend something to a policymaker, or we need to bring out some hidden pattern that we have seen in our community. So usually resort to causal relationship, establishing causal relationship between two variables or three variables. So when you write down a simple linear regression model like this, and you estimate your betas, don't forget that when you estimate your betas, the error term vanishes. Why? If we had done the mathematics, you see that when we are like deriving the formulas for betas, you minimize the error term, like kind of we are minimizing the error between the y and the real y and the predicted y that we have. So when we minimize it, the formulas that comes out is the like beta naught, y bar, all those formulas. So we kind of use the error term to derive those formulas. It's part of the computation that we just did. So you cannot see the error term there, but yes, we use it in the computation for beta naught and beta 1 because we minimize that error, the sum of squared error of that. Okay. So how should we interpret it? We are going to do them one by one, always, starting with beta naught. Beta naught tells us the average value of y when x is 0. Like when x does not exist, then when you put 0 here, we get what? Beta naught. So you can think about the conditional expectation function that we started with, where some estimation, like expected value of y given x is equal to beta naught times beta 1x. So if x is equal to 0, then we are left with beta naught. So the average value of y is what? Beta naught if x is equal to 0. So that's how we interpret beta naught. When x is equal to 0, average value of y is equal to what? Beta naught. Now, beta 1 is the most important, arguably, interpretation that we are interested in here because it kind of captures all other things being equal. It captures the causal relationship between the variables that we are trying to establish. So our variables are x and y. We want to see how x affects y. So when you find the change in y as a result of a change in x, you get your beta 1. So in a sense, if x goes up by 1 unit, y also goes up by what? Beta 1. So the unit will depend on the kind of like question that you are trying to ask and the context and the data that you have at hand. So let's look at some examples to maybe really grapple with it. Okay, so suppose we fit this kind of model. Like we are using the value that we calculated for where beta naught was 10 and beta 1 was 2. How should we interpret this kind of model? Okay, so starting with beta naught, we said that beta naught is the average value of y when what x is what 0. So if no one is in the class, when class size is 0, the average test score is what 10. It doesn't make sense. Yes. So usually, in some cases, you see that the betas, like beta naught, the intercept doesn't make sense, but we are really interested in the slope coefficient because this, if no one is in the room, then the class size, the average test is going to be 0, right? But this is just a hypothetical situation. And the slope coefficient, which captures the causal relationship, or other things being equal, measures if class size increases by 1 unit, which is by 1 student. The unit is what? 1 student. The test score, the average test score will increase by 2. Don't forget that change in y over change in x. So if x changes by, which is the class size, changes by 1 unit, y, which is the test score, will increase by beta 1. And in our case, beta 1, hello. So the interpretation is that if class size increases by 1 unit, test score will increases by 2. So it means that you can advise a policymaker that you must increase the class size and the test score, the students will perform well. Obviously, that doesn't make sense, yes. So what if the slope coefficient was negative? Then it means that when class size increases, test score falls. This kind of makes sense because when the class increases, the teacher-student engagement reduces. So it will affect our test scores. So it depends on the kind of value that you get, you interpret it. Any questions so far? Or any suggestions or maybe anything to point out?
Yeah, hello guys. Please, if you have any question, you can let us know. Yeah. Gabriel, please, we can continue. I think we don't have any questions so far.
Okay. So,
Also going right.
okay. So from this question above, okay, let's move forward to other examples. What if we fit this kind of regression? Consumption is equal to 1.23 plus 0.456 income. And how should we interpret the beta naught and beta 1? Again, beta naught measures the consumption, average consumption, if income is 0. That is, if you don't have any income, you spend on average, the people that you are analyzing spends on average 1.23, maybe Ghana cedis or maybe dollars or anything that the value or the unit that you are measuring these variables. In economics, we have a name that represents this kind of estimate, which is the intercept of the consumption function. And it is called the autonomous consumption. That means if you have no income, whatsoever, how much are you going to spend? Autonomous. It doesn't depend on income. So if you have no income, it means that income is equal to 0. And therefore, what you spend is at $1.23 or cedis. So this represents the autonomous consumption. Now, how should we interpret the slope coefficient? Again, the slope coefficient tells us how the change in independent variable affects or leads to a change in the dependent variable, how much. So if income increases by 1 unit or 1 cedi, $1, average consumption will increase by maybe 0.456 cedis or dollars. It depends on how you are measuring everything. Another thing, let's say we want to find out how hours of study affect the CW of students? How should we interpret it? So again, if the student studies for 0 hours, zero, doesn't take a book, on average, their CWA is what? 36.67, which is they are not graduating, right? And the coefficient how measures if like hours increases by 1 unit, how much will your CWA increase? So when you are studying, when you measure your study hours per semester, if you increase it by 1 unit on average, how much will your CWA increase? So in this hypothetical situation, our CWA increased by what? 1.935. So now I think we are all abreast with the interpretations. If you have any question, you can ask. Okay, so moving on. Now, we are done with our interpretations. Are we done? The obvious answer is no, we are not done because we need to really think about our estimates and really see whether they are really credible or there are some hitches somewhere. Are we sure that the coefficient, this coefficient that we have here, really captures the causal effect or the unique effect of hours on CWA? Again, are we sure that this 0.56 is the causal effect or the unique effect of income on consumption? Aren't any other variables affecting these estimates? So the slope coefficient can only be interpreted as causal effect if and only if, again, if and only if there are no confounding variables affecting both the dependent variable and the independent variable. What do I mean by confounding variables? Confounding variables are hidden variables. They hide behind and they are causing, like they affect both the dependent variable and the independent variable. And they'll be causing some trouble without us seeing it. So how does it play out? So let's kind of read this. So regression is like trying to determine who is speaking in a room with two people at the same time or at once. If one speaker, the confounder, is hidden somewhere where in the error term, you may mistakenly attribute some of their words or some of their effect to the visible speaker, the F explanatory variable. Likewise, when the confounding variable is omitted, regression cannot distinguish its influence from that of the explanatory variable, so the estimated effect is distorted. What does this mean? Okay, so suppose we write down our simple linear regression model, income as a function of education. Can we conclude that the beta one, that is, if education increases by maybe 1 year, how much will income increase? Does it really measure the causal effect of education on income? Are we like confident about that? And from the previous slide, we can only say that if there are no confounding variables. And from our thinking and from labor economics, we can say that there are other factors that really affect education and income if we really think hard about it. Let's suppose that ability of individuals are different. Yes, they are. And they affect how much education that you get and your income too. So it means that the ability, which is also in the error term, correlates. There's some relationship between ability and education, right? So that means the effect, which is the beta one, does not represent only the effect of education on income, but ability also is hidden here. So from this analysis or explanation, we can conclude that beta one does not measure the unique effect of education on income because we want to know how only education affects income. But there is a hidden variable, which is the ability that affects education and affects income. So we cannot really disentangle the relationship to really know the actual effect of education on income. Therefore, we have to account for that ability that we are seeing. Again, there are other variables that we have to include. You don't have to resort to education and income and then go away and interpret that, okay, beta one affect the causal effect. Otherwise, our beta one will be biased. What does it mean? So for example, let's say our beta one is 10, and obviously the education correlates with ability. It means that the 10 that we are getting is not the true value or the true causal effect of education on income. It is biased. So when you advise a policymaker that this so and so, you are giving the person a bad advice because the regression, the results that you are getting are not credible. So whenever we are running our regression, we need to really think about like regression, the variables, which variables to include, and if there is some correlation, our results. Okay, this assumption I didn't want to bring, but let's make this assumption. Beta one only represent the causal effect, and this assumption is part of the OLS assumption, like ordinary least squares assumptions that we need to check. It only recovers the causal effect if there is no correlation between the error term and the X. If there is no correlation, then we can be sure that beta one is the unique effect of education or the independent variable on the dependent variable. So how about the CW? Can we say the same thing for it? Does it measure the unique effect? No, because the other variables that affect hours of study, for example, motivation of the individual, your motivation affects the number of times you study or the number of hours that you study, and it also affects your CW. So we cannot really measure only like the hours of study, the unique effects, to be very, very difficult. So there will be some correlation between hours of study and the error term because motivation is also found in the error term, right? So this situation is kind of called endogeneity. So in the future, maybe we talk about that. And there are other methods, for example, instrumental variable that we use to really disentangle this effect. So for now, we are not going to go there. We are just building on our like foundation. So how should we do it? To solve this problem, we have to control for the confounding variables. We need to admit that they are there. We need to control for them so that we can actually disentangle the effects between the dependent variable and the independent variable. We need to account for them. So how should we account for them? We have to include them in the regression by getting data for all these confounding variables. But thinking about it, it's very, very difficult to really get all the confounding variables because we don't know which variables are also affecting them. Very, very difficult. But if you are sure that you can really, really get all the variables, and even some variables are not even measurable. For example, ability, how can you even measure ability, right? So in that situation, OLS becomes a little bit problematic, right? I hope you are thinking about these kinds of things that we are encountering. So when you include extra independent variables to the X that we already add, then we are moving from simple linear regression model to multiple linear regression model. So to see that we have our dependent variable here, our beta naught, our beta 1, then we have our normal X, beta 2, we have another parameter because we have included other variables that we need to, and everything, then we have our beta naught. Note, we have to control for all the necessary ones because if you omit one, it will be very, very difficult. And how should we know like this variable affect the other? We have to resort to economic theory. What is the theory saying? Which variable should we include according to the theory? And is that variable measurable or observable? Can we get them? So these are the kind of challenges that researchers face normally when we are doing our analysis. Okay, so I think next week, yeah, we would do a lot of maybe data examples and see how estimators works, and hopefully we tackle some other topics that we have like hypothesis testing, confidence interval, and the rest. Okay, so let's do some extensions. we are moving back to the simple linear regression model where we have only x and y. What if we have log, all our variables are logs? We log them. Yeah, sometimes you decide to log some of the variables because they are too big. Provided there are no negatives in there, they are too big. So you log them. So when you see log in the dependent variable, when you log the dependent variable, and when you also log the independent variable, then how you interpret it changes. Our beta naught will be similar to what we did. If log of x is 0, then log of y will be beta naught, right? But our beta 1 has a special interpretation. We can now interpret our beta 1 as elasticity, because elasticity is the percentage change in x over percentage change in y. But when you log them, you can actually interpret the beta 1 as elasticity. I didn't show the mathematics because I want the mathematics to be very minimal. But when you find the change in log of y over the change in log of x, it will approximate the elasticity. So we interpret beta 1 as elasticity. That is when log is here, the log is here. What if this place is not logs, it's level form, but we have log here? How are you going to interpret it? So this is kind of maybe an assignment, maybe next week. We call it semi-elasticity. So when you go and you read about it and see how interpret semi-elasticity. So as an example, let's say we log consumption and we log income. How are we going to interpret this kind of model? Again, the intercept, which is 46.8, measures the average log consumption, which obviously doesn't make sense when log income is 0. So usually we don't resort. We are very, very much interested in the beta 1, but sometimes too, some people are really interested in this. If there are no logs, then this represents what the autonomous consumption, and this represents what the marginal propensity to consume, right? Okay, so since there are logs, we can interpret it as what the beta 1, which is 13.72, as the elasticity. That is, if income changes by 1%, consumption will increase by 13.76. Why increase? Because it is positive. If it were to be negative, then if income increases by 1%, not 1 unit, 1%, consumption will reduce by 13.72%. That's how we interpret elasticity, a percentage change in this as a result of a percentage change in what that. Okay, so we now know how to interpret level form when there are no logs. We know how to estimate them using our OLS estimators. We know how to interpret them, and we know when and where we can interpret the beta 1 as causal effects, and how the R estimate is very problematic if we don't consider the confounding variables and the rest. So our last thing that we are going to talk about is when the independent variable is not maybe consumption values like, or income values like 13 point whatever, $2,000, whatever. What if the independent variable is binary? That is, it is 2, 0 and 1. We can represent them as 0 and 1, 0 and 1, depending on which one you want. Then, okay, so for example, educated and not educated. When you get your data, you ask the person, are you educated? No, 0. Are you educated? Yes, 1. So that independent variable will be binary 2. Male or female, smoker, non-smoker, whatever. Any variable that is binary, like is 2, then we can use the dummy variable regression. And the interpretation is also a little bit different, like the log plot. But it's not very, very difficult. So let's go through it quickly and then see where time permits us. Okay, so to fix ideas, let's consider that like X is gender, male or female, and we let X to be equal to 0 if female and X is equal to 1 if male. how should we interpret that income model, which is this? If X can be one, which means the person is a male, and S can be zero, which means the person is a female. You can choose either one, but the interpretation will be different depending on which one is zero and which one is one. And the category that is zero is called the base category, or comparison category, depending on what you want to call it. That's the base category. And the one will be the other. We don't really have a name for it, but it's the other category that we consider. Okay, so if male, female is zero and male is one, how should we interpret our income model? So our beta naught will represent the income of the base category, that is female, because female is equal to what? Zero. How true is it? If here X is zero, then this whole thing will vanish, assuming that we have estimates for this. Then there will be no error term, right? Then this whole thing will vanish. Then we are left with what? Beta naught. So the value for beta naught will represent the income of the average income of females. That is the base category. What about beta one? Does it also represent the value of income for males, which is the other category? The answer is no. This represents the difference between the base category and the other category, which is what? The male. The difference. So if here is positive, then it means we are going to add beta 1 to beta naught in order for us to get the income for males, which is here. And the income for females is what? This. So if here beta 1 is positive, then it means that the income for males is larger than the income for what? Females. But if beta 1 is negative, then the income for females is larger than the income of what? Males. So in essence, we are kind of measuring inequality here, or other things being equal. So if this is positive, then it means that there is some inequality between the income of males and the income of females. But if it's negative, then it means that females on average earn more than males. Okay. Any questions so far? Any question? Because our time is almost up.
Yeah, I still
Any,
don't see any questions. So, Gabriel, please, you can continue. Yeah.
okay, so this is where my time, here is where I want to end. So next week, we will sort data and then hypothesis testing and the rest, everything else will follow. So I think I didn't go over my time. I wanted to restrict everything to 1 hour.
Yes, you didn't go over your time, and this is really
Yeah,
perfect. Thank you so much. I hope
okay.
that our audience have benefited enough. So this is just a reminder to all of you who are here with us. So before you came, I was saying that we are starting this beginning econometrics class because we want you guys to be able to understand the kind of papers that our guests normally, present, right? But then to be able to understand that we have to start from somewhere to be able to get to the advanced econometrics. So we are moving slowly from the beginning. We go to intermediate, then after that we go to the advanced econometrics. So when we get to the advanced econometrics, then we'll be looking at the various types of estimations when it comes to actually, writing papers, correcting for the co-founders, and like various ways by which we can do that, right? And hopefully, going through the series, you get to know how to do that so that you can write a cogent paper and make some good econometric analysis. So thank you so much, Gabriel, for your presentation, and we look forward to host you again next week so that you can take us through the practical data session. So please, if you still have any question, you can, Gabriel is still here. You can ask him before we end this program. Okay, I think we don't have anything. Gabriel, if you have any last words before, I know we are going to see you again next week, but in case you have anything to say before you go.
Hmm, okay. What I would just say that tell other people that you have started. Yeah,
Okay, okay,
tell
okay.
people that if we have already started, so they should join. And next week we are going to look at the practicals of everything and maybe dive into it. I didn't want to go over my time, so I didn't push a lot of things here. So next week we are going to
Okay.
add other things to like our script. So see you next week.
Thank you. And also, this session is
Okay,
recorded, and
okay,
we are going to send a link to the YouTube so that everyone can have access to it. Thank you so much, and have a wonderful night. And bye bye. Thank you. Bye.
okay. All right.